Okay, yeah, as I said, these collections of slides is what I'm going to go through, what I will look at right now. So this was the first collection of slides, and my focus is now on UML and the different kinds of diagrams that are available in UML. So yeah, the central diagram is definitely the class diagram, which you see over here for the social network. Apart from classes, the classes involve the attributes and the operations. Apart from classes, you see associations, and the associations may be association classes, as over here, or as a special form of association is a part-whole relationship. This is the whole, this is a part, and this is a strong part-whole relationship. This is a composition. The class diagram concepts, one important class diagram concept is generalization, which is presented over here. So in a chess game, there are various characters which can be a pawn, or it can be a knight, or a king, or a queen. The triangle here always points to the more general class, and the more special class is found on the end of the open triangle here. The strong part-whole relationship is indicated with a black diamond. The weak part-whole relationship is indicated with a white diamond. The strong part-whole relationship is the composition. The weak part-whole relationship is the aggregation. And both part-whole relationships indicate, as the name says, a part and a whole. The game is the whole, and the game has two parts, namely two players over here. And a player owns a part of the player are the figures, the characters. So a player owns and owns up to 8 pawns, and these pawns are part of the player during the game. So that's about the class diagram. The object diagram represents, for a particular and given class diagram, a point in time that where concrete objects are indicated, and where concrete objects constitute it quotes an example state. So here for the profile class, you have 1, 2, 3, 4 profile objects. For the association class friendship, you have 1, 2, 3 friendship link objects. For the association class commenting, you have one commenting object that is attached to a link. To a link that connects a posting and a profile, as the association class commenting requires. And this is a link object, because it is at the same time a link, and it is also an object because it has properties, because it has attributes. This is a link from a part-whole relationship, so the posting exclusively belongs to a particular poster. Okay, that's the object diagram. The UML also involves so-called use case diagrams. The concepts, by the way, the concepts of the main concepts of the class diagram are always the main diagram. The main concepts for the diagrams are always stated after the first example of the diagram shows up. So here we had the first class diagram, and here you see the concepts that show up in a class diagram. And these are the concepts: class, attribute, operation, operation parameter, operation return type, binary, association, association class. We had a reflexive association, we had a composition, and we had in the association the concept of a role, the association name, the multiplicities in the association. Yeah, these are the concepts in the class diagram. Here are some more concepts of the class diagram. The concepts in the object diagram are the object, the link, the value, and objects, manifest classes, links, manifest associations, values, manifest attributes, and link objects, manifest association classes. Yeah, you have an instance level in the object diagram, and you have the type level in the class diagram. In the use case diagram, you have the concept of an actor, of a use case, of use case relationships, the include and the extend. The use case diagram is not supported in use, but in use supports the state chart diagram. The state chart diagram in the protocol state machines that are available in use, you can specify the order in which the operations of a particular class are allowed to occur. So this is the protocol state machine for the class profile from the social network example. And here in this particular protocol state machine, you say and you specify the init operation is the first operation that is going to happen, and then the other operations can appear in an arbitrary order here. The order of the operations is restricted by the preconditions as well. But here in the state chart diagram, you explicitly say the init operation occurs as a first operation, and it only occurs once. This is what you specify here in the state chart diagram in the protocol state machine. The concepts in the state charts are that you have state invariance, you have an initial, you have a final node, you have an initial state, you can have a final state, you can have normal states, you have transitions. These are the arrows here. A transition usually has a form that you have a guard, you have an event, and you have a postcondition. Guard and postconditions are OCL conditions. The event and the transition from one state to the other state only takes place when the event occurs and the guard is satisfied, and the transition only takes place when the postcondition is also valid. But the postcondition and the guard are optional in specifying a transition, as you see here in the transitions. Over here you only have events. The state charts determine object life cycles, and what is determined here with the protocol state machines are the respective operation called sequences. Yeah, the two classes, the profile class and the friendship class, have quite different state machines, quite different state charts. So there's an infinite number of operations possible here for the profile objects, but for each friendship there is only a finite number of operations possible for each friendship object. The next diagram that we have been discussing was the sequence diagram. In the sequence diagram, you have concepts like object, like lifetime. You have the activation of a lifetime where something is going on in the object. You have a message representation, and you have a link representation for the use representation of the link in a sequence diagram is that it shows the link as an object. So we have a small sequence diagram over here. This is the actor, this is the use shell, which sends operations and which invokes, the use shell invokes operations on particular objects. So as you see here in the respective command list, the first three actions were to generate three objects, and then on all three objects an initialization action is done, and the init operation is executed, and then some invites and then some declines here happen. So the sequence diagram, the sequence diagram represents the message flow, the messages that are sent between the objects. So for example, you see here a message that is sent from the Putin object to the respective friendship between Putin and Trump, and this friendship that was established. This friendship was established by the respective operation here, Trump invite Putin. That message created here the friendship objects. The friendship object. An equivalent but different form of diagram that shows execution of messages is a communication diagram. So the same actions, the same communication between objects that is displayed here, in form of a sequence diagram. The same communication is displayed here in form of a communication diagram. So you see here exactly 9 operations, and these 9 operations, or these 9 commands are the same. The sequence diagram, you have lifelines for objects, and the messages, the order of messages is specified in a geometrical way, typically from top to bottom. The time advances and the message order is reflected in the communication diagram with a numbering system. So you have here again what was presented in the sequence diagram here with the lifelines, Merkel, Putin and Trump. So 3 lifelines for 3 objects. These 3 objects are represented here in a way more similar to an object diagram, and the execution of messages is specified here in a numbering system, and the messages are explicitly written down, and you see also the direction in form of an arrow, a direction that indicates that a message is sent from a particular object to a different object. So for example, this decline message that went from Putin to the friendship object, this decline message is exactly this message that is specified here from between Putin and the friendship. So you have here particular concepts. I mean, you have objects, you have message, you have a message number, and you have a link representation, again similar to the representation of an object. Okay, sequence and communication diagram can be compared to each other. As the last diagram I want to mention in the UML, the activity diagram. The activity diagram can be used for representing the implementation of an operation. Activity diagrams are very close to flowchart diagrams, and in activity diagrams you can specify control flow. So, for example, when you have here the init operation, which basically initializes the attribute first n, last n, and user n from the profile class and it manipulates these attributes with particular parameters of the operation, then you can represent exactly this order in which the attributes are manipulated here with an activity diagram in this form. In activity diagram, you also have a split of control with the fork, and you have a union of a split of control flow and a join of control flow. So in this case, a different activity diagram would be that you could specify here in the activity diagram that these assignments could be done in parallel or in what order soever. So the flow of control is distributed here into 3 different threads, and the 3 different threads are joined here again. Activity diagrams are not currently supported in use. This is a more complicated example for activity diagram, and I think that was for the diagram part, that was what I wanted to mention here about UML. In use, we have the option to give implementations for operations, and this is done, and the implementations of the operations are done in the SOIL language. SOIL stands for Simple OCL like Imperative Language. It's kind of a programming language where you can create objects, and you can destroy objects, you can create links, and you can destroy links. You have variables which you can assign a particular value with an OCL expression. You have control flow, you have a loop, you have a while, so you have a for loop, you have a while loop, you have an if-then, and you have an if-then-else. You have recursive calls of operations. And you can use these SOIL statements in a use file for operation definition, and you can use SOIL statements on the use shell for ad hoc actions, and you indicate them in a particular way. I think this was what I wanted to say about this part here. For the slides in this part, this is already about the OCL expression, which I will come to later. I will now directly jump to the OCL data types. The most important slide probably here in this collection of slides was the specification. This was a specification of the data types. Namely, you have 4 data types in OCL: real, integer, string, and Boolean. And here you also see an example for the use of the generalization mechanism in UML. So integer is a subclass, a subtype of real, and all data types are subtypes, are subclasses of the OCL data type, of the OCL type OCL-NE. And you see here the particular operations that are available on the particular data types. And so this was more or less the declaration of the data types together with the declaration of the operations. Here you have, on this slide, you have example terms, example expressions for the respective operations. And on the next and following slide, you have an explanation of the operation in form of a verbal textual explanation of the particular operation. That was already the part on the data types. We have been discussing in a special collection of slides the different kinds of associations that are available in UML. The classification that I've been taken here was a following one. We have binary association, we have the association class, we have a reflexive association, we have ternary or more general n-ary associations, we have aggregations, we have composition, we have functional associations, we have qualified associations, and we have derived associations. And all these kinds of associations were present in this example of the student world. So the ordinary binary association, that was this association attendance here. The association class, in particular for association with attributes, was the association tutorial between student and course, where the association has an attribute, namely the student gets a particular payment, gets a particular salary for giving the tutorial, and this salary is not modeled as an attribute of the student and not modeled as an attribute of the course, but it is modeled here as an attribute of the association and therefore the association becomes an association class. We have reflexive association. A reflexive association is an association where one class participates twice. We have here we have many reflexive associations here, but in particular we have a reflexive association here on student that is called knows by name, and in the role names are knower and known. And here you see, reflexive association means that one class participates twice, namely in the role of the knower and in the role of the known. The ternary association, or more general, the n-ary association. The ternary association is over here. That's the association examination, which is between a student in the role of the examinee and two employees, one employee takes the role of the examiner and the other employee takes the role of the recorder. So here we have the ternary association. The aggregation is a weak part-whole relationship with a weak binding of the part to the whole. The weak form of part-whole relationship, you see it over here. A course has particular former courses which can be regarded as part of the course, and the weak part-whole relationship here indicates that one course can be a part of two other courses. One course can be a part of two other courses, and that's the weak part-whole relationship. The strong part-whole relationship is a composition, the strong binding between the part and the whole, and the strong binding is found over here. Namely, homework can be part of a course and a homework can be part of a project. Both sides on the black diamond have here the 0.1 multiplicity. So a homework can be part of at most one course and at most one project. And what sits here in the black diamond is the exclusiveness. A part that is connected through a black diamond exclusively belongs to the black diamond. So a homework cannot be at the same time a part of a project and a part of a course, although the multiplicities would allow this. A homework must, first option, exclusively belong to a project, then it does not belong to a course. Second option, a homework exclusively belongs to a course, then the homework cannot belong to the project. So this is what sits here in the black diamond. And this is also one difference between the weak form of part-whole relationship, where a part can be shared, as we have seen also in the example. A functional association is an association which has multiplicity 0.1 or 1.1. So for example, a homework in this modeling has exactly one author, so this is a functional association here. A qualified association is an array-like construct with qualifier attributes. So there is a qualified association between server and student, and the particular point about the qualifier attribute, the login here, it's kind of an attribute of the association, not an attribute of the server or an attribute of the student. But in particular, this multiplicity is valid only for the combination of server and login. So when you have a given server and you have a given login, then this determines either no student or one student. So this multiplicity has to be read as given a combination of server and login ID. In general, the server will have many students, but this multiplicity only applies to the combination of server and login here. So this is qualified association, and the last association kind, that's derived association with in form of an OCL term. The derivation is done, and this determines a path in the class diagram, is my saying over here. So the derived association is this association between tutor and student, and the path taken here and the derivation rule is stated over here. So this derived association is basically the path that you first you navigate two associations. You first use the role name tutored, and then you use the role name attendee. So you start from the student, and then you use the role tutored, and then you use the role attendee. So the path that is mentioned here is exactly the path that from student you go to tutored, and then you go back to student over the attendee, and this sits over here, and due to typing reasons you have to apply the as set here as well. So that's a derived association. That was a derived association. Let us jump into the special discussion on the commonalities and differences between association, aggregation, and composition. We have here in one class diagram all three association kinds. So we have a plain association, we have one aggregation over here, and we have two compositions, and we have indicated with particular multiplicities. So the association has multiplicity star star. The aggregation has multiplicity 0, dot, or 2 on the whole side, and star on the part side, and the multiplicity here on the composition is 0, dot, dot, 1. So a person is recorded either with the mother is not recorded, or a person has one mother, and analogously a person, either the father is not recorded, or a person has exactly one father. And what we have been doing there, we have been in these slides, we have been discussing the commonalities and the differences, and the main idea is expressed over here. So for the association, you do not have any restriction on the kinds of object diagrams you are allowed to build. When you are using the aggregation, when you are using the white diamond, the weak form of part-whole relationship, you have to build the object diagrams, have to be acyclic. Cyclic object diagrams are possible for associations, but cyclic object diagrams are not allowed for aggregations. So for aggregations, you require the object diagrams to be acyclic. And you also require acyclic object diagrams for the composition. In this example, for fatherhood and motherhood, these are the compositions. And in addition to requiring acyclicity for the object diagram, you forbid sharing for the composition. So the homework cannot be shared by the project and by the course. And here in the example, the child cannot be shared by a father and a mother. When you want, in this modeling, when you want to model both the father and the mother, then you have to model only the mother with the black diamond, and you will have to model the father with the white diamond, or the other way around. You model the father with a black diamond, and then you model the mother with a black diamond. So these cases, for example, modeled here. That's okay. Here you model the mother with a black a red diamond, and you model the other relationship that must be the father relationship here with a white diamond. And the general rules sit in this table. Okay, the last part about the diagrams was we had a discussion on the relationship between the class diagrams and the object diagrams and the OCL invariants. So the basic, this is a recapitulation of the basic class diagram concepts. This is a recapitulation of the basic class diagram concepts, of the basic object diagram concepts for classes and attributes, and we had a similar discussion for the basic object diagram concepts with respect to associations. And as a summary, we have stated, in order to emphasize the relationship between the class diagram and the object diagram, you have given one particular class diagram, and the interpretation, the semantics of the class diagram is a set of all valid object diagrams. And how you achieve an object diagram, it is expressed over here. For each class you have a finite set of objects for that particular class, and for each attribute you have a value assignment for the attribute in the object, and each association is interpreted as a finite set of links. And when you have, in addition, when you have given invariance, then you restrict the possible set, the allowed set of object diagrams further. When you have given and defined invariance, then you restrict from all possible object diagrams, you only consider those object diagrams in which the invariants are true for all objects. And that's that's this strong relationship between the class diagram and the object diagrams. The object diagrams give meaning, give interpretation to the class diagrams and to the invariants. The invariants further restrict the allowed set of object diagrams. Yeah, and I think this is what we have been discussing here in connection with UML, and the short formulation is that we have been discussing class and object diagrams and state machines and sequence diagrams and collaboration diagrams, and in particular in class diagrams we have these various form of associations, the plane association, the aggregation and the composition, and we also have the association class. Next we will discuss and recapitulate what we have heard about OCL.